Okay, well, let's introduce Isaac Newton and state some of his laws of motion that govern all of our study of mechanics in this first semester of physics. You may associate Newton with being hit in the head by an apple and developing his law of gravity. But that's just one of several laws developed by Isaac Newton in his lifetime. He was born in 1643, lived until 1727, and died at the age of 84. In his 30s, he, alongside Leibniz, independently invented or developed the language of calculus. During that time, he also was prolific in the study of optics and the use of telescopes, and devised many laws regarding the nature of light. There's also something known as Newton's law of cooling in the study of thermodynamics. But he's probably most known for his seminal work, the Principia, which was published in 1687 at the age of 44, which set out all the laws mostly involving celestial mechanics, but really governed and described all the laws of motion. So in this unit of study, when we refer to Newton's laws, we're not talking about Newton's law of gravity, Newton's law of cooling, Newton's corpuscular theory of light. What we really mean when we talk about Newton's laws are Newton's laws of motion, but we'll just drop that phrase. Okay, so there are three of them: Newton's first, second, and third laws. The first law is often referred to as the law of inertia. I'm going to skip the second law and just give you a name for the third law. We can call the third law the law of force pairs. No object has ever been hit without hitting back in return, so to speak. If you knock on a door, your knuckles hit the door, and sure enough, the door hits your knuckles. Newton's second law is best stated as a mathematical equation, and it really has to do with answering the question, what if an object is not in equilibrium? What if the sum of all the forces acting on an object don't come out to equal zero? And we know the result is the object will change its state of motion. In other words, it will accelerate. And the question is, how much acceleration should we expect? So Newton's second law tells us that the acceleration is directly proportional to the net applied force, and at the same time, inversely proportional to the inertia. Actually, we can state this a little bit better. Instead of ACC, we'll just say A for acceleration. I like the symbol we've given for the combination of all forces. And inertia, well, the only quantity that gives an object this property of inertia is the object's mass. So there we have it. That's a statement of Newton's second law of motion. Oh, and I should add to it that acceleration and force are vector quantities, whereas mass is a scalar quantity. This equation can be algebraically rearranged to say the combination of all forces is found by multiplying the product of mass and acceleration. In fact, we might want to say it like this. If we want to find the acceleration of an object, we'll divide the force by the mass. If we want to find the force applied to an object, then we'll multiply the mass and acceleration together. And lastly, if we were trying to do an experiment to determine the mass of an object, then we could apply the equation by dividing the force by the acceleration. Okay. Well, in this lesson, I just want to focus on the first two laws. So often Newton's first law of motion is stated thusly: an object at rest wants to stay at rest, and an object in motion wants to stay in motion. But we can say that more succinctly. We can say the natural tendency of any object is to maintain constant velocity. So that covers objects at rest. An object at rest has a velocity equal to 0. And if that object at rest stays at rest, then it's maintaining a velocity of 0. And of course, an object in motion has a particular velocity vector pointing in some direction. So this could be a car driving down the highway. If the ground pushes up as hard as gravity pulls down, if the resistive forces are exactly canceled out by the forward applied forces, then the sum of all forces would be equal to 0, and the car's desire would be just to continue in a straight line. To follow a curve one way or the other on the road would require an imbalance in the forces in some direction. So an object doesn't just maintain constant speed, it maintains constant velocity, right? Both speed and direction. So this idea of natural, I guess natural means when no net force is applied. Okay, so like we said, then the second law says, well, what if a net force is applied? What if the sum of all forces doesn't equal 0? So Newton's first law really tells us what must happen to an object that's in a state of equilibrium. When an object is in a state of equilibrium, it's either going to stay at rest or it's going to continue to move in a straight line with a steady speed. So the second law says, what if the object is not in a state of equilibrium? And as I said earlier, the result is that the object must accelerate in the direction of the applied force, and the amount of acceleration goes down as the mass of the object goes up, and vice versa. So it's important we write the equation in its full form like this. It would be shortcutting it to say A equals F over m. We're never interested in any singular amount of force acting on an object. We're always interested in the combination of all forces. And we have to treat force as a vector quantity. I can illustrate that by pointing out the behavior of an object on an incline. What are all the forces that would act, maybe on an ice block? Some of you might be familiar with the, I wouldn't exactly call it a sport or a hobby, but the activity of ice blocking. That's where you go to the grocery store or a neighborhood liquor store and you find a large block of ice they sell these, I guess, for people who are throwing big parties and need a giant ice block. You can buy them and use them to make a poor man's sled. So you put a beach towel on top of the ice block, you sit on it on a grassy hill, and next thing you know, you go accelerating to the bottom of the hill. Okay, well, how could we find out how great that acceleration is? There's a few forces we'd have to take into consideration. And I might be getting a little bit ahead of myself, but I want to give you an appreciation for the vector nature of force. So the pull of gravity is straight down toward the center of the earth. It's not down toward the bottom of the incline. The motion will be toward the bottom of the incline, but the pull of gravity is directed vertically. At the same time, there are a few other forces acting. There's the force of contact between the incline and the ice block. And then there's going to be some amount of air resistance and friction. We'll just combine those. We'll show those each individually. Maybe that vector is air resistance, and maybe this vector is friction force. Okay, so to figure out what the acceleration is, we're going to have to find a way to combine all these vector quantities together. And as you learned in our previous study of two-dimensional motion, the best way to add vectors together is to break them into their components or put them in unit vector notation to figure out what the resulting effect is. So just a quick introduction to Newton's first two laws. The first law informs us about the motion of objects in a state of equilibrium, and the second law informs us about the motion of objects when they are not in a state of equilibrium.